Okay, so we're going to take a look at antiderivatives. So this is the definition. Function capital F of x is an antiderivative of f of x on an interval if capital F prime of x is equal to f of x. So basically, you've got a function. And I'm just going to give you a really simple function, 4x to the third. And so we say that capital F of x is an antiderivative of little f of x if its derivative is equal to that. So the function that would satisfy that would be x to the fourth, because when you do the power rule on this function, you get 4x to the third. Okay, let me fix this 3. So that's a pretty simple concept. Now, notice though that this isn't the only antiderivative. You can say that we have other antiderivatives. If you guys can think of one. Other antiderivatives. Ooh, derivatives. Okay. For example, x to the fourth plus 2 is 1. Can you think of another one? I sure can. X to the fourth plus 7. What about x to the fourth minus 5? Because every time you get the derivative of any one of these functions, the derivative of the constant part is always going to equal 0, so it's always going to equal to this guy right here. So what we say is the general antiderivative of 4x to the third would be x to the fourth plus c, where c is any constant. Okay, so c can be any... Okay, so let me make a little picture. So this is my x and y axis. And this guy right here, I'm going to graph 4x to the third. Now this is, of course, a very rough sketch, but I'll just, look something like that. 4x to the third, roughly. And then x to the fourth plus c, what this means is this guy right here, well, x to the fourth looks, something like this, sort of like a flatter parabola kind of a deal. But this isn't the only one, so this is also, you can have another antiderivative right below it. Now these are supposed to be copies of each other. Obviously, I need to improve my drawing skills, but you guys get the idea. So, for example, this would be x to the fourth minus 5, and so on and so forth. This one's x to the fourth. But all of these are antiderivatives. Okay, now let's take a look at some of the rules. Okay, so first, before we go through some of the rules, let's go through some notation. This is notation that we're going to use a lot later on. And so I'm just going to say that when you write down this guy, this is called the integral. If you write down the integral of f of x dx, and we're going to explain exactly where this comes from and how these are related, but for now let's just say that this symbol right here, which is called the integral of this function, is asking you to find the antiderivative of little f, which is capital F of x plus c. Okay, so over here, let's start putting down some of the rules that we're going to be seeing. First, let's do the power rule for integrals. So the power rule for integrals basically says if you're getting the integral of x raised to a power, all you have to do is you're going to basically do the opposite of the power rule for derivatives. So you're going to add 1 to the exponent, and you're going to divide by that same exponent. So, for example, we just did one that's similar to that, but let's say you want to find the antiderivative of x to the 7th. So what you would say is this is equal to, x to the 7th dx. You would add 1 to the exponent, which is going to be 8, and then you're going to divide by that same number, and then plus c. So this is the antiderivative of x to the 7th. Now, it's important to note that this does not work for n equals to -1. You'll notice that if you try to do it, what will happen is if you try to get the antiderivative of x to the -1, you would add 1, which would give you 0, and then dividing by that same number, this is bad news. So there's its own rule, and so let's write it down right here. This is the antiderivative of 1 over x. Okay, so let me write it down. Let's use the same color. No, slightly different. Okay, so the integral of x to the -1 dx, or the integral of 1 over x dx, is simply, well, you're looking for the function that when you get the derivative of it, it equals to 1 over x. Well, we know that to be the natural log of x. Now, I want to write down natural log of the absolute value of x, and then I'll explain later where this. So plus c. Okay. So far so good. Let me put a little line through these guys. Okay. All right. So far we've got those two rules. Then we also have the sum and multiple laws. Sum and multiple. And those are, just the basic, same as the derivatives. If you're looking for the antiderivative of the sum of two functions, all you have to do is find the antiderivative of the first function plus the antiderivative of the second function. And then also, if you want to find the antiderivative of a constant multiplying your function, this is equal to the constant times the antiderivative of your function. I forgot my dx right here. Okay, so for example, let's say I've got the integral of 5x to the 3rd minus 7x squared dx. So basically what these two laws are telling me is that, one, this constant I can just not pay attention to it, just leave it there, times, and then I can find the antiderivative of each one individually. So this one, for example, I'm going to use the power rule on this guy, which means I'm going to add 1, so 4 divided by 4, and then minus, again, 7 stays, x to the 2 plus 1, which is 3, all over 3, and then don't forget your plus c. Okay, so this is my that's my answer for that guy. Okay, so let's continue. Let's take a look at some trig rules. So for the antiderivative of sine of kx plus b dx, this is just going to equal to negative cosine of kx plus b all over k. So here, let's do an example. And this, I mean, this is just basically the opposite of finding the derivative. So if I want to find the integral of 2 sine of 4x minus 3 dx, this is equal to the 2, remember, stays there. And the antiderivative of sine is going to be negative cosine. The inside is going to stay the same. And then divided by that number 4. And so think a little bit about where that 4 comes from. It comes from basically the backwards chain rule, right? Because when you get the derivative of cosine of 4x minus 3, you have to multiply by the derivative of the inside, which means you're going to multiply by 4, and then the 3 is just 0. So you need to balance that out. And you can always test these. Here, I'm just going to simplify it real quick. But you can always test any one of your answers because all you have to do is find the derivative. So this guy is just going to be negative cosine of 4x minus 3 over 2 plus c. And so if you get the derivative of this guy right here, you should get 2 sine of 4x minus 3 back. So that's the point. And let me just write down. So for example, cosine is very similar. You can find all of the rules in your book, and in the formula sheet that I have for you. Let me give you guys another one. How about secant squared x dx? So think about it. Press pause and think about it. What's the function? Then what you get the derivative of it equals to secant squared. Okay. Yep, you're right. If you thought tangent, you would have been absolutely correct. Ooh, I forgot the plus c over here. Okay. Now let's take a look at one more. What about the integral of e to the kx plus b dx? So remember, when you get the derivative of the exponential function, it equals to itself. Now here, the only consideration you have to make is that it's the same thing. It equals to itself, except that if there's a number multiplying the x, you would have to then divide by that number as well. So for example, if I have the integral of e to the 3x minus 4, this is equal to itself, e to the 3x minus 4, but then all over 3 dx. And so those are the basics, and there are a few more, but those are the main ones for now. Now another way to think about antiderivatives is the solution to the simplest form of differential equations. And so a differential equation is just an equation with derivatives in it. So for example, I'm going to just give you a very simple differential equation. So we've got, let's say you want to solve dy over dx is equal to 4x to the third. Okay, so basically what this is asking you for, the solution to this differential equation is, it's not a number like you're used to when you solve other equations. It's actually a function. So what this is asking you for is it's asking you for the function that when you get the derivative of it, it equals to 4x to the third. So another way of thinking about it is, well, that's just asking you to find the antiderivative of 4x to the third, which we know to be x to the fourth plus c. Now, very commonly, differential equations come along with what are called initial conditions. And these are, this is information that you have about your function. So for example, let's say I've got, in this same example, my initial condition is that y of 0 is equal to, let's say, 2. Okay, so this is my initial condition. So what this is telling you is it's giving you specific information about the x and y values of your function. So it's saying that when x is equal to 0, y is equal to 2. So what do you think that's going to be useful for? Well, plug them in and you'll see that what this allows you to do is to solve for c. So that c, that constant that at first was, just any constant, is actually in this case a very specific number. It's the number 2. And so your solution then in this case is y equals to x to the fourth plus 2. That's the solution to this differential equation right here. It's an actual function. Okay, so let's do an example of an application of this. We've done these problems before, but we used an equation that we didn't explain where it came from, and actually now we can explain with antiderivatives. So we've got a stone that's dropped off the top of a building and hit the ground with a speed of 120 feet per second. Okay, so let's draw our little building here. And then let's say that we're up here, right there. And hopefully this is a building in construction and there's nobody there. But we drop it off. And so we're trying to find the height of the building. Okay, so to find this, we remember the relationship between position, velocity, and acceleration. Remember that to go from position to velocity, you get the derivative. And then to go from velocity to acceleration, you get the derivative of that. So then to go backwards, if you know the acceleration, which we do in this case because it's gravity, we're going to find the antiderivative. That's going to give us the let us go from acceleration to velocity. And then if we get the antiderivative of that, we're going to be able to get the position, which is going to help us find the height of the building, which is what we want. Okay, so let's start off with acceleration. So we always start off with acceleration. We know that acceleration is equal to negative 32 because gravity is 32 feet per second squared. And it's negative because it's going down. So the velocity then is going to be simply the antiderivative of negative 32. And then I'm going to put dt here. Now you always need this one, and later on we'll explain what this represents. But for now, just trust me that this guy always has to be there. And the antiderivative of negative 32 is simply negative 32t plus c, right? Because the derivative of negative 32t is equal to negative 32. Okay. So then, well, what we need though is some initial condition. I need to know what's going on with the velocity there. So the velocity at 0, this I have to get from the problem. I know that the velocity at 0 is equal to 0 because it says that the stone was dropped. So that means that I didn't throw it, it was dropped. So the initial velocity was 0. So that means that when t is equal to 0, v is equal to 0. Which means, so you just basically plug in 0, set this equal to 0, and so you would find that c is equal to 0. Okay, so in summary, v of t is equal to negative 32t. So we've got our acceleration, we've got our velocity, and now, since we're looking for the height, that's the position. So let's find the position. Okay, so I erased all that other stuff over there. So let me do position here. So the position function is simply equal to the antiderivative of the velocity, which is negative 32t, and then dt again. Okay, so the antiderivative of this guy is negative 32t by the power rule, t squared over 2 plus, now I'm not going to use c because I already used c, so I'm just going to use d. Okay. Now, here I'm in a bit of a pickle because I don't have my initial condition for the height of the building. So that's actually what I'm being asked. What's the height of the building? Which would be the initial position, obviously, right? So in reality, what I'm looking for, what the question is asking me, is for d. The only information that I do have is that it hit the ground with a speed of 120 feet per second. That's information from the velocity. So if I plug that into the velocity, I would get that 120 is equal to, what happened to my pen? That's just weird. Negative 32t. Okay, I fixed it. So t is equal to 120. Actually, it's a negative 120 because it's going downward, so the velocity is negative. So the time is negative 120 divided by negative 32, which is 3.75 seconds. Okay, so what this tells me is that it took 3.75 seconds to hit the ground. Well, what's the position at 3.75 seconds? So what this means is that the position at 3.75, since that's when it's on the ground, that means that this is equal to 0. So then if I'm looking for d, what I need to do is use this guy. Let me break this guy up. And I need to plug in for t 3.75 squared over 2 plus d is equal to 0. Sorry about messing that up a little bit. And so if I solve for d here, I would get 225 feet. And that's it.